title of the PDF is Time Response Transient Response of RC First Order System. So we have seen the RC First Order System. The same things are shown here, whatever I have shown in the previous case. So just if it is visible, you let me know. Okay, Chaitanya is saying it is visible. I think I'm audible also. So I'm going to show you the same thing, whatever just now we have done. Okay, I'll show you. So this is the same RC first order circuit, V in S and V output S, and then I'm finding V output by V in 1 by 1 plus RCS. Now V in is equal to UT, V in is equal to 1 by S, so V output is V in into 1 by RCS, so 1 by S into this. And likewise, if you go, you'll be finding V output is equal to 1 minus e raised to minus t by tau into UT, where RC is called as tau. Definition of time constant is given. And this is the response that we are finding, that is output response is 1 minus e raised to minus t by tau. So this is a slower system. This is a slower system because in this case we are finding tau value is quite high, and whereas this is a faster system, more steeper response of output, but tau value is slow. So lesser is the value of R. In that case we are finding tau value is less and system will be faster. Next, let us go for the second order system. Okay, I think the second order system is also visible. Just say yes in the chat box if this PDF is visible. Okay, second order system. Okay, so let us start with second order system. This is little complex but fundamentally same. Again, you can check that the output is taken across a capacitor. So C has become 1 by CS, L has become LS, and this is R. So what is V input? It is R into R plus LS plus 1 by CS into IS. So the same thing we have done in case of force voltage analogy in case of transfer function based transfer function finding of RLC circuit. So that one proof will be used in many different cases. So this is the RLC circuit in Laplace domain. In this case, I am trying to find out the voltage across capacitor and what is the ratio of output voltage and input voltage. So voltage across capacitor will be 1 by CS into IS. Voltage across voltage input voltage Vin is equal to R plus LS plus 1 by CS into IS. So just find out what is V output by V input. Same thing we have done previously. So V output by V input is 1 by CS into IS, R plus LS plus 1 by CS into IS. So if you just cancel IS and then rearrange a little bit, what we are going to get is 1 by LC S square plus R by L into S plus 1 by LC. So this is the transfer function. This is the first step, first question in the first part of the question for finding the step response of second order system. So whatever was CT by CS by RS, here I am writing as VOS by VNS. So this is same as CS by RS. So next line I have written the standard second order system equation. So this equation V output by Vn is same as omega n square plus S square plus 2 zeta omega n plus omega n square. Omega n is undamped natural frequency and zeta is nothing but the damping factor. Okay. So all those things are not much required for us. So we are just skipping this part, and we are finding that there are 4 cases. So this part is very important. Zeta is equal to 0. This is called no damping or undamped. Zeta greater than 1, it is called as overdamped. System is very slow. Zeta less than 1 and greater than 0. So zeta less than 1 means zeta is in between 0 and 1. In that case it is called underdamped, and zeta is equal to 1. In that case it is called as critically damped. So these are the 4 cases possible. There are many equations, that is omega d is equal to omega n into root under of 1 minus zeta square and all. So all those things are not very important. What I'm doing is I'm just trying to find out what is the how to find out the final equation. Final equation, that is what is VOT, or what is nothing but CT equation that I am trying to find. So you can come here. So CS by RS, whatever equation we had found previously, this case in terms of RL and C. Okay, so these 2 equations, V output is V in S and CS by RS. This equation is, so this equation 1 by LC S square plus RLS 1 by L, this is equated to the standard equation. So below omega n S square 2 zeta omega n S plus omega n square, this is the standard equation of second order, and whatever is given here, this is the equation of RLC circuit. Now these two are equated, and from there, so this is what I'm finding from there. So just check. V output S by V input S is equal to like this. So this proof of determining CS I have not asked. I just want to show you the steps. So this is CS by RS is this omega n square. Then find what are the pole. So today morning only we have seen S square plus 2s plus 10. Okay, so the same way you are supposed to find out what are the roots of the equation, and the root will become complex conjugate. So here also the root has become complex conjugate, and substitute RS is equal to 1 by S. So CS is equal to 1 by S into this, and from there if you are just going, only you have to remember what is the equation of CT. So if you are seeing that this is the CT equation, so this is one equation that you have to remember, or easier than that, or like this. So here this is the output equation of second order RC circuit. So this one equation you have to remember, that is 1 minus e raised to minus zeta. So if zeta is equal to 0, in that case this part will become 1. Okay, so 1 minus, so everything in this equation is in terms of zeta and omega n, if you just check. Okay, so CT with 1 by S, CT with unit step input, as we did in previous case. In this case the equation becomes bigger because this equation is actually a very complex equation. Either you can write this equation or you can write this equation also, that is 1 minus e raised to minus zeta omega n t sine alpha cos omega dt cos alpha sine omega dt. So in that case this 1 by root under of zeta square and zeta you are writing in terms of sine alpha and cos alpha. So there are a lot of things, and most compact form is given at the below. So this proof is not asked generally in the exam. Directly what you can write is, so first up to this point, that is first this thing. So how is this thing coming? B naught S by BNS. Okay, and then from here CS by RS is equal to this. Then take RS in the right side. CS is equal to 1 by S into this, and directly you can write down. We are taking the inverse Laplace transform, and we are finding CT. And by saying that, directly you can write down this equation. So CT is equal to 1 minus e raised to minus zeta omega n t 1 minus zeta square sine omega dt tan inverse root under of 1 minus zeta square by alpha. So likewise, so then there are 4 different cases. So in that equation, if you are substituting different value of zeta, then what happens? So in that case, this is a very good study what is done. So first you are supposed to write down that equation. So this is a characteristic equation, you can say denominator equation, and from S1 to, so if you are just solving that characteristic equation, you are finding there are 2 roots. Today morning also you have done the same, only here we are doing it by the means of a symbol. You just substitute zeta is equal to 0. So first case, under damped condition. Under damped condition means zeta in between 0 and 1. You can substitute 0.6. Okay, you can substitute 0.6 and you will be finding that you are going to get 2 poles like this. So the poles will be imaginary poles. So if you are substituting 0.6 here, 0.6 square is nothing but 0.36. 0.36 minus 1, that is 0.64 minus. So here you will be finding plus minus j8, j.8 likewise. Okay, so here you are going to get 2 conjugate poles if the zeta is less than 1. In the same roots, if you are substituting zeta is equal to 0, if you are substituting zeta is equal to 0, this part becomes 0, that is zeta omega n. This part becomes minus 1, so it will be plus minus j. So in that case, the poles will be on j omega axis. So just check where zeta is equal to 0. Just check here, zeta is equal to 0. That means this will be plus minus j omega n. So whenever it is undamped, at that time the poles of the system will be on j omega axis. So whenever the poles are on j omega axis, it will be producing a sinusoidal response. Third case, whenever zeta is greater than 1, at that time you will be finding the roots are real and positive. Here you substitute greater than 1, substitute, you can substitute zeta is equal to 2 or 3 or 4. You will be finding that the roots of the system will be on the left hand side of the real axis. And if zeta is equal to 1, zeta is equal to 1 means you will be finding S1, 2. So both the roots are on the same position. So both the roots are on the same position means both the roots are exactly on the same position, which is called as minus omega n. So what you are supposed to find out is, first find out the transfer function, then compare it with the standard transfer function. From there you find out this poles S1, 2, and in this pole substitute 4 values of zeta. 0, something in between 0 and 1, 1 and something greater than 1. So whenever you are substituting zeta value something in between 0 and 1, you will find two complex poles. Whenever you are substituting zeta equal to 1, you will be finding two real poles at the same position. Whenever substituting zeta greater than 1, you will be finding two real poles but in the left hand side, stable poles. And whenever you are substituting zeta is equal to 0, at that time you will be finding the two poles are on j omega axis. Now the responses are also asked, that is, if zeta is less than 1. If zeta is less than 1 means complex poles. Complex poles produce under damped response. So this is actually one very important response. We will see this thing in the next lecture. Then what is the under damped response? Under damped response means zeta can be 0.3, 0.4, 0.2 likewise. So in that case, what is the response we find? It is the input is step input. Okay, so the response goes up and oscillates along the unit step amplitude and then gets steady. So what are the time characteristics in this? We find there is delay time, there is rise time, there is peak time, there is settling time, percentage peak overshoot, all those things we find here. Okay, so this is the underdamped response, and this kind of responses you are supposed to draw for zeta in between 0 and 1. If zeta is equal to 1, if zeta is equal to 1 means two poles on the same position on the left hand side. So two poles on the left hand side means the system is stable, and as the two poles are on the same position, you are going to get a critically damped response. This critically damped response is almost looking like a step response. Now third case, when zeta is greater than 1, at that time you will be finding the two poles are on the real axis but at different positions. At that time the system will become slower. Okay, so this case, if you see this response, this is very steep kind of a response. In case of critically damped, this is a faster response. That means the response is almost like a step response. So response is output, and what is input? Input is 1. So this is the step input 1, and output is this one. Output is almost like a step input. So that is critically damped, that is zeta is equal to 1. For zeta is equal to 2, 3, 4, 5. So more you are increasing the value of zeta, flatter will be the response. Flatter means it is very slow kind of a response to reach the output. And lastly, when zeta is equal to 0. When zeta is equal to 0, we found that both the poles are on j omega axis. So whenever there is a complex pole on j omega axis, that produces a oscillatory response like this. So this is called undamped natural response, or this is called sustained oscillation. And this underdamped response, this is called damped response, okay, where damping is in between 0 to 1. And this is critically damped, and this is overdamped. So this is a characteristic you have to remember for different values. What is going to be the characteristic of the second order system? So what are things to write? First thing, you are supposed to draw the circuit diagram RLC. Then you have to prove that whatever is the V output by V input transfer function in case of RLC, that is 1 by LC into A square plus 2 zeta omega, and in terms of L and C. Then you have to compare it with the standard second order system response. From there you have to find the two pole equations, and in those two pole equations, if you keep on substituting the value of zeta, then you are going to get all these four responses. And finally, what is the equation of CT? CT equation you can find like this. So in this case also, if you are substituting different value of zeta, exactly all the previous responses, whatever you have obtained, same response you can obtain. So this is the output response of second order underdamped system with step input. CT is also called as transient response of second order system in case of underdamped condition. So when the zeta is in between 0 to 1, this is called underdamped. When zeta is equal to 0, it is called undamped. Zeta is equal to 1, critically damped, and zeta greater than 1, it is called overdamped. Undamped response is fastest, overdamped response is slowest. So this is the underdamped response. This is another thing which we will do, which will not do anymore because I'm telling you now itself. So this CT is equal to 1 minus e raised to minus zeta omega and t by this. So this is a characteristic. In this case, you can substitute any value in between 0 to 1. So you can substitute 0.3, 0.4 or something, and you are going to get this kind of transient response. So initially this is called transient part, and after this steady state point, this is called steady state part. So in transient part, we are finding oscillations. Initially the oscillation is very high. This part is called as peak overshoot, and as the time goes by, this oscillation is dying down, okay, and this is coming to the stability. So there are different times we can find out here. Initially, it is starting from 0 and going up to the peak value, but wherever it is crossing this 1. So what is this 1? 1 is nothing but the input. So you will find that at this point, the output is exceeding the input and going beyond. So exactly this point is called as rise time. So rise time is time taken by the response to reach to the 100% of the output value. Okay, so that thing is called rise time. Wherever the output is reaching to the 50% of the 100% value is 0.5. This is called as delay time. So TD, TR, TP. Wherever the output is reaching to the peak value, this is called as TP. And wherever it is reaching to almost 0.95 of the input of the output and staying within that band. Okay, so the output, final output is equal to 1. You can check that. So this thing is oscillating across the value 1, and finally it is coming and getting steady at 1. So steady state error is equal to 0 because final output value is 1. Okay, but here initially it went beyond the 1 value, again came below, again the oscillation is little bit less, so where it is reaching to the 0.95 for the final time and not coming out of that thing, that point is called as 5% settling time. If it is 0.98 and not going beyond that, it is called as 2% settling time. So settling means amount of error is reducing. Error is nothing but here the error is maximum, because the final output value is 1 and here suppose it is 1.36. Okay, so how much is percentage overshoot? Percentage overshoot is 36%. If this amplitude percentage MP is 1.36 and output value is 1, so maximum deviation occurs at peak time, so that is 36%. So percentage MP will be 36%. Okay, and that percentage is reducing. So after reducing, whenever it is almost 95% of the output, so 0.95, okay, there it is called as the system is almost 95% stable or 5% unstable. After going here, suppose this point the output is 0.98 and then it is getting stable. So this 0.98 where it is happening for the final time, this point is called as 2% settling time. So all these time characteristics you have to explain with their equation. So what is meant by delay time? It is the time required for the response to reach to the 50% of the final value. That means 0.5. So TD is given by 1 plus 0.7 zeta by omega. What is the rise time? This is the time taken by the system to reach to the 100% of the final value. So pi minus theta divided by omega d. Omega d is equal to omega n into root under of zeta square minus 1. Omega d is called as damped natural frequency. And theta is equal to tan inverse root under of 1 minus zeta square by zeta. So this, all this theta, omega d, all are function of omega n and zeta. And while calculating all this thing, you have to keep your calculator in radian mode. Okay, so this pi radian, don't consider this pi as 180. This pi is equal to 3.14. This theta also has to be calculated in radian. So here theta value is given, tan inverse root of 1 minus zeta square by zeta, and omega d is equal to omega n into root of omega n 1 minus zeta square. So what is omega n? It is called undamped natural frequency. Unit is radian per second, and zeta is not having any unit. Zeta is equal to r by 2 into root under of c by l. Likewise, then delay peak time, wherever the peak of the underdamped response is achieved, that is called as peak time and given by pi by omega d. So pi is 3.14, omega d is omega n into root under of 1 minus zeta square minus 1. Settling time, 1 minus zeta square actually. Settling time, it is the time required by the response to reach and stay within the 2% band. So there are actually two definitions of settling time. One is 2% settling time, is 5% settling time. 2% settling time is given by 4 by zeta omega n. So 2% settling time is greater than 5% settling time. So 2% settling time is 4 by zeta omega n. 5% settling time is 3 by zeta omega n. Finally, what is peak overshoot? So if the peak value is 1.36, it is 36% above the input unit step 1. So we can call that, if peak value is 1.36, percentage MP is actually 36%, and the equation of that thing is given here. So these are the 5 characteristics that you are supposed to explain. So this page, these 2 pages are there that you have to write. This is called as the transient response of second order characteristics. So three very important questions we have done just now. First one is the first order RC circuit. What is the transient response? First we are supposed to find out the transfer function, then we have to give step input as the input. We have to find out what is CT and then plot CT, define time constant. Second case the same thing, second order RLC circuit, give the find out the transfer function, then give unit step input, find out what is the output equation CT. It's a very big equation, and then compare it with the standard second order transfer function, that is equation in terms of zeta, omega n and all, and there you find out what are the second order pole equation likewise. Okay, and in that pole equation you have to substitute four different values of zeta, 0 in between 0 and 1, 1 and greater than 1, and you are going to get four different pole positions. Okay, likewise, and all this pole position is going to create four different responses of CT, that is unit step response of circuit for four different zeta. So if zeta is equal to 0, we are finding the response is oscillatory. If zeta is in between 0 and 1, we find it is undamped or it is damped oscillation. So oscillation is not sustaining. Here the oscillation is sustained. Here the oscillation is decreasing, and it will come to a stability. Okay. Then zeta is equal to 1. In that case, it is almost output is almost same as unit step input. It is called critically damped, and zeta is greater than 1. Here the system response is very slow. This is called over damped response. So this is the second question. Third question is if the system is under damped, then what is the response looks like? So response looks like divided into two parts. One is the transient response, another is the steady state response. In transient response and steady state response, there are five different time characteristics, that is delay time, rise time, peak time, percentage, MP, that is peak overshoot, and settling time. And there are two settling time, one is called as 2%, one is called as 5%. And 2% settling time is more stable compared to 5% settling time. So these were all that we have covered today.